And the next presentation is going to be almost the opposite end of the spectrum. It's to explore or provide you with some understanding of the design community, the structural design community. After that, we'll be followed by some presentations relative to the semantic web technologies to then give some of the material scientists and the designers a little bit better appreciation for what the capabilities are associated with semantic web technologies. And then with all of that information intact, as we go into the breakout sessions, you guys will have all the answers for all the pieces to the puzzle to create all the answers that we need as we move forward. So I'm looking forward to some great solutions here in the workshop. Ray Maloney is from, I actually want to say Air Vehicles Director, but that's done by the wayside.
Yeah, but Aerospace Systems.
Yeah, so propulsion director and Air Vehicles Director combined about a year ago. And we work in the area of structural design for air vehicles, typically more in the area of conceptual design than in the detail design.
Yeah, conceptual preliminary design. Thank you, Claire. And the acronym down at the bottom there, MYSTIC, stands for Multi-disciplinary Science and Technology Center. As he mentioned, I'm in the Aerospace Systems Directorate in the Aerospace Vehicles Division. And what I am going to talk about is the complete other end of the spectrum, and in particular, vehicle level. We were down at the material, down at the atomic level, molecular level, now going all the way up to the full vehicle level. I want to give you a few definitions that I think are worthwhile. You know, what is multidisciplinary analysis and optimization? And what we're doing is we're trying to couple multiple engineering disciplines to account for, discover, and exploit new phenomena for system analysis and optimization. So we not only want to account for it, we want to take advantage of the coupling if we can. And then the next question is, well, what is high fidelity? Or we also call it appropriate fidelity. And this goes back to actually one of the slides of the previous presenter. We don't want too much, we don't want too little, we want just the right amount. And the right amount, as we define it, is to capture the physics that is driving the design. Not only in what disciplines that we couple together, but also what level of fidelity, and I'll try and define fidelity for you here, that we use in an individual discipline. Now that might sound like an easy thing, but for the most part we don't know. We typically use rules of thumb and experience to determine what disciplines we have to couple to capture the physics, and then what level of fidelity we have to use in an individual discipline. So this is kind of difficult to read, but I just want to talk a little bit about fidelity, because we talk about fidelity levels. And at the very top here, we have fidelity level 0. And that information is typically historical information, empirical information. There is no analysis behind it. It's just regressions through data that has been achieved from vehicles that have been built in the past. And as we work our way down to fidelity level, I'll focus on the structural area. We go from 1D bending load, and then level 2 is limited 3D finite element analysis, and then level 4 we're talking about maybe 100,000 to several hundred thousand degrees of freedom to represent the structure. And you can look over here on the far right, aerodynamics, anywhere from scale and empirical information, we get into linearized panel methods, then down to nonlinear CFD methods, and then you can almost get all the way down to numerical simulation as well in terms of level 4. So that's how we classify fidelity levels whenever we're talking about engineering analysis. And we're trying to get away from, in the primarily conceptual design today, uses zero-order fidelity. They don't actually bring physics into the design process until later. So we're trying to work our way into at least level 1, but trying to get more into level 2 and 3 fidelity whenever we do our engineering designs. So this is a slide that I stole from Pam Coker, who's sitting in the office, in terms of the acquisition cycle or the digital thread. And this just tells you where we're playing in the acquisition process, and it's primarily back here. It's highlighted in red, concept development or conceptual development of an aerospace vehicle. It's more about developing technologies, multidisciplinary technologies, and assessing the impact of those technologies on the vehicle, and developing methods that allow you, methods and processes to allow you to incorporate and account for those technologies early in the design process. So we want to make better informed decisions early in the process. So we're trying to develop and trace technology to mission-level capability impact based on physics. So if you start over here in the far left, we're actually pretty good at developing technologies. We got a lot of smart people that think of wonderful ideas. So different types of technologies and multidisciplinary technologies, things like active elastic wing, flutter suppression, advanced materials, which we're talking about here, thrust vectoring, things of that. Technologies are very easy, or not easy, but we get a lot of good ideas. The next level is that, well, we are pretty good at, if we're using physics-based analysis and design, we can determine the engineering impact, meaning that what the impact the material has on the weight of the structure that we can account for or calculate. So weight reduction, some aero technologies, what impact does that have on drag reduction? So we can quantify computationally the impact on engineering capabilities or engineering parameters. But really the Air Force doesn't care about that. You work your way up the Air Force chain of command. What they're really interested in is mission capability impact. Kills per dollar, IDs per dollar. What does it cost me to sustain it? You know, what are the life cycle costs? Those are the types of things that the Air Force leadership wants to talk in. So we need to be able to map our technology into mission capability. And what we really want to find is the partial derivative of mission effectiveness with respect to the partial derivative of technology. All right, so at a very high level, that's what we're trying to do. So we're developing multidisciplinary technologies, multidisciplinary methods to account for those technologies in the design process. But in the end, from an Air Force perspective, it's what does this technology do for my mission? So how do we bring the high-fidelity multidisciplinary design into pre-milestone A in the acquisition process? And we're trying to do, I'll talk about the KPPs later, but first of all, whenever you do traditional conceptual design, which you have here, is that you pick a technology suite, and they typically represent it with what they call K factors. They're just knock up and knock down factors on these conceptual equations. And it's very easy for them to do thousands of configurations at the conceptual design level, and that's 0th order of fidelity. No physics are included in it. It's just based on historical information for the most part. Then what they do is that they will down select based on whatever information they got from the conceptual studies, and typically they only pick one, maybe two configurations to do this high-fidelity physics-based assessment on those configurations. That's a problem, because they're making decisions early on in the process, and down selecting, they're not informed based on physics. It's just based on historical information. And a lot of the configurations and technologies that we're trying to evaluate do not appear in the historical databases. The new configurations. You know, it's a hypersonic vehicle, it's a joint wing vehicle, it's a tail supersonic vehicle. None of those have ever been built, so there's no historical data to tell us how those will perform. So what we want to try and do is bring tens of configurations forward to do a detailed design or preliminary design and assessment based on physics instead of one or two, which industry does today. And that's what this KPP, there's two up here. We want to reduce the design cycle time, but also we want to bring, say, 15 configurations forward with the same resources. Whenever we make this statement to industry, they say, oh, I can bring 10 forward, just multiply my budget by 10 and I'll be fine. Well, that's not the answer. We have to be able to do that assessment with the same amount of resources in the same amount of time. So, also at the conceptual design level, we're talking about materials here. How do they represent materials? Well, they don't. They either say that it's metallic or it's composite. And if it's metallic, they don't put any factor on the weight equation for the vehicle. If it's composite, they'll say, well, maybe it's going to save me 15%. So they'll go into the weight equation, put 0.85 on the weight equation, and away I go. That's how they address materials at the conceptual level. Now, at the higher fidelity assessment, so we got a model for design first, and then we do our analysis for design. Again, this is the appropriate level of fidelity. At least at this point, we're actually calculating the vehicle response and the mission capability based on physics. And the way materials is used here is that we'll start picking materials. So we need material properties. But we're not designing materials. We just need the material properties, the E, the G, strain allowables, stress allowables. That's the type of information that we use to bring forward into the design process here. So we'll prick a material and then we'll evaluate how it performs. So once we're able to do analysis for design, then we do design space exploration. Whenever we talk about design parameters here at this point, we're talking about aerodynamic design parameters, plan form, airfoil parameters, things of that nature. Then also structural topology, how many ribs and spars do we have, and then sectional properties. What are the moments of inertia? What are the thicknesses? The vision would be, well, how do we bring some of those material property design variables into this process? So we can actually design the materials at the same time, not just pick a given material. And we call that multi-scale. So we're doing multidisciplinary, but if you want to start bringing material properties design variables in, now you have to add multi-scale into this process as well. So the other thing we do is that after we're able to do this high-fidelity assessment, we do testing as well. We want to determine whether or not our methods are working properly. Do they predict the performance that's properly that we're trying to get? And then also we want to test configurations. Does that joint wing configuration actually give us the weight and the drag that we were predicting? So we're about getting more information, get better information, and get it early in the process so we can make these informed decisions so that we can tell the Air Force leadership, okay, which technologies do you need to invest in to get the capability that you want at the mission level. So at a high level, what are we trying to do? Well, we're really trying to merge conceptual design with aspects of preliminary design, because it's at the preliminary design level that you start seeing that level 1, level 2 fidelity starting to come into the process. Conceptual design has a level 0, but a lot of the design parameters at the conceptual level are the aerodynamic parameters that are frozen. So the configuration is frozen, then we're just left with some of the structural parameters of the design. We find that to be suboptimal. But here you just see some of the disciplines that we're working on and considering. We've done a lot of work coupling aerodynamics, structures, and controls. We're now starting to bring propulsion in over there in the far right. EEWS is engine exhaust wash structures. Anybody that's familiar with the B2 app deck problems know what the coupled physics and the problems are associated with that. System thermal management is a big deal. We don't do cost modeling, but we know cost is important. We have to consider it. And then you see down there in the right-hand corner, materials is on there. How do we bring materials design into this design process? And that starts leading to not necessarily multidisciplinary, but multi-scale. So what's the impact if we're able to do this? Well, we have classified impact into two areas, scientific impact and acquisition impact. Scientific impact is that if you can exploit that synergism of those mutually interactive disciplines through the coupling, you can produce a capability that cannot be obtained otherwise. And there's a few examples here. The X-29 is a forward swept wing. What they had to do here was couple aerodynamic structures and controls to create a weight competitive forward swept wing. You cannot get that capability without coupling those disciplines. Another one there, this is the X-53 in the middle there, that's the active aeroelastic wing demonstrator. What they produced there was the roll performance of a vehicle by coupling aerodynamic structures and control, while reducing the weight of the vehicle considerably and increasing the drag. And that increases, or decreasing the drag increases the range. And then over on the far right-hand side there, I have the F-22. They actually used what's called aeroelastic tailoring, which is using composite materials to manipulate the deformed shape under loads that gave you better performance of the vehicle. So here are examples of what has been done, and we believe that if you're going to get hypersonic vehicles, high-altitude long-endurance, strike tanker, tail supersonic, there's no way you're going to get those capabilities unless you do this multidisciplinary coupling. The other impact on the far right over there is that, well, if we can bring physics earlier into the design process, into the analysis, we can reduce the discovery of late defects due to physics. And the B2 app deck I already pointed to, they did not design that properly because they couldn't analyze it properly because they weren't considering enough physics early in the design process to capture the phenomena driving the design. And every one of those vehicles over there had some problem associated with not being able to model the physics that were driving the design. In particular, it's the loading environment, be it the aerodynamic loading, the thermal loading, the acoustic loading, and the coupling between those disciplines. billions of dollars to deal with those problems. So I've got about 5 more minutes. I've got a few more slides. Here are some studies that also show you what the impact is of coupling these different disciplines and taking advantage of it and increasing the fidelity. The first, so we're looking at total gross takeoff weight of some tailless vehicle, and we're looking at subsonic radius. So we want low weight, high radius, right? So we really want to be here on the plot. If you use traditional design methods, this is the plot that you get, okay? And it's actually pretty close to linear. If I'm trying to increase range, I increase total gross takeoff weight. Well, if we add some of these multidisciplinary technologies, and the first one is active aeroelastic wing technologies, which is coupling aerodynamics and controls in a static sense, you can get a vehicle that performs like this. We got lower weight for the same range, and then if you include active flutter suppression, you again get even a lower weight and a greater range. But look at the configuration. You start to see a much higher aspect ratio. Oops, lost the cursor. A much higher aspect ratio wing than you see in this configuration here. And so this shows you that coupling these disciplines produces a different configuration altogether. Now, the one thing that I want to point out, I'm exaggerating a little bit, but what you don't see is you don't see a design for the zeroth order at this point here. And the reason is that it was unattainable. It would not close. You'd have to change the configuration drastically in order to get that performance. So really, the weight savings here is infinite compared to traditional design because we were able to take advantage of the coupling of the disciplines. So another example of this is the impact expanding on the design space. We're just expanding the design parameters that are available. We have some engine parameters, engine cycle parameters, wing parameters, constraints. So if we just do a conventional conceptual design, we just have these 3 parameters, and we get a gross takeoff weight of around 68,000 pounds. If we start increasing engine cycle parameters, just these additional parameters, now the weight comes down to 66,000. And if we further increase wing parameters, we can get a final weight there of about 62,000 pounds. And then if we start adding a couple of technologies, we can get a further reduced weight, again, showing the impact of using physics-based calculations and expanding the design space with degrees of freedom and the impact that that has on mission performance capability. And then here is another demonstration of these coupled physics. The top figure here is nonlinear aeroelastic analysis. This is the coupled physics, but it includes active aeroelastic and active flutter suppression technology. And this is, this is baseline technology here. This is AAW and active flutter suppression. What I want you to watch here is the wing root bending moment, because that's what we're trying to address. We're trying to do the same flight maneuver, but we want to reduce wing bending moment, and you'll see that we also get a significantly reduced weight. So this thing's doing a 9G pull-up, and we're using the control surfaces to alleviate or manipulate the load, and it reduces the wing root bending moment by, I think it's like 30%, which means we can reduce the structural weight based on it. So 32% reduction and 24% reduction in vehicle weight. We can't do this if we cannot couple the disciplines in the design process. But these computations here are considered to be level 2 and level 3 because we're using computational fluid dynamics, and this takes days to run. I think I'm about out of time, so I'm going to just jump to the end here and just tell you where the bottlenecks are. Gaps to achieving this desired process of multidisciplinary, large-scale multidisciplinary design. You know, we need rapid development of the models. We need to be able to couple these disciplines and account for them in physics-based methods. We need a computational framework that supports this, and that is the monster of all acronyms. That's multidisciplinary, multi-fidelity, multi-scale, analysis and optimization with uncertainty quantification. We want to be able to do all those things with this. And we need to put uncertainty and probabilistic design methods in, and really changing the culture is going to be a huge issue. So this is just a a laundry list of some of the technology, more specific technologies that we're after, but I'll be happy to answer any questions.
Greg, we sat down a while back and talked about trying to capture some of the knowledge that is associated, I believe, with the empirical portion of the fidelity level 0. And you had some comments about the ability to capture some of that knowledge using various approaches.
Yeah, we've spent some time trying to capture what's called the design intent, and we've used inference engines in the past, and we've interviewed a lot of designers to try and capture that information and then create knowledge-based engineering design capability. And I've made 2 attempts at that, back in the late 90s and then again, early 90s and then again in the late 90s, early 2000s. You just can't do it. You know, trying to get into these designers' heads and trying to capture their experience and all that information, and then try and put it in a form that can be put into a system and then obtain, like I said, I tried it twice and I failed twice. So we believe that use the physics, try and do your calculations and decisions based on physics. And we're getting fewer and fewer designers available too, because we design fewer and fewer airplanes. You know, people that are retiring now probably have the opportunity to work on 4 or 5 airplanes. People that are going to start designing the next generation airplanes, because it takes us 25 or 30 years, they might get to work on 1 or 2 airplanes in their career. So the experience base is yes.
Just follow up on the comments about the designer. The Procter & Gamble is really kind of like the premier ICT of the empirical design system. They simulate everything except doing these thoughts. If they can figure out how to do that, they do it too. Those guys know. So it's a tough problem.
Yeah, in our simulations, like I said, when you start getting the 2nd and 3rd order fidelity, you're talking about hours, days, possibly weeks when you start copying the physics.